Hello, I am Leticia Morais and I'm from University of Brasilia, Brazil, and I did a second at the University of Strathclyde in the UK with Professor Alessandro Tarantino, and my research is about analytical and numerical modeling of the problem of hydraulic fracturing. And what's the hydraulic fracturing? The hydraulic fracturing is a method that was initially created to determine the in situ stress of rocks. And this method is also used to stimulate wheels in the gas and oil industry, and what it does is to increase the production of the wheel. And how does it do it? It increases the permeability of the wheel, fracturing the rock. But there is a particularity about the shale gas, because it is essential to use this technique to make it possible to produce this type of reservoir, because it has a very low permeability. The shale reservoir is called unconventional wheels, and the hydraulic fracture will enable the production of them. So, how does the hydraulic fracture stimulate the wheel? The hydraulic fracture creates fractures on the rocks, which will change the flux regime of the reservoir. The flux regime will no longer be radial but linear, and it can also connect pre-existing fractures, and it can make areas of the reservoir that were not connected with the wheel be connected, increase the production of it. And this technique is very efficient, but there are some challenges of using it, and the biggest main issues for us and for the people who have interest in using it is, first of all, there is the environmental problem, and that's why the hydraulic fracture is very discussed all around the world. And the main environmental problem is the contamination of the soil and the underground water resource by the fluid that is used to fracture the rock. But there are many other effects, as the air pollution and the need of use big quantities of water to do the technique. About the geomechanics problems, the main issue is the design of the fracture, where we need to know the length of the fracture which is being created and the open of the fracture, so we can know from those what is the productive of the wheel. It is also need to know the flow rate that has to be injected to generate the fracture of the length and the width that we want. So if you inject too much fluid, we can create a very large fracture which could reach an area that were not intended to, generating an environmental problem. Or if the flow rate is not big enough, the production of the wheel will not be increased. The other challenge about the hydraulic fracturing is to know how it affects the stress field and what problems it can generate, and also the reactivation of faults, where the hydraulic fracture can reach a fault and induce many problems with its reactivation. So, after understanding the hydraulic fracture, we try to model it, and there are two possible ways we did it. The first one is the analytical solution, which, as far as I know, some of the solution is used in practice, and basically these analytical solutions try to solve the equations of balance of mass and flux in a very well defined geometry, like an ellipse or a rectangular, and those shown here. And that's the geometry is the main difference between them. I used the PKN model to model the hydraulic fracture, and I had some interesting results, but as we were not satisfied, we decided to study the problem using the numerical approach. To model the problem with this numerical approach, first of all, we needed a couple of the hydraulic and mechanical equations, and there are already many programs that do that. But the second thing we needed when working with fractures is, because of the fracture generates discontinuities in the displacement, stress and strain field, we need something to deal with it, and there are some techniques to treat that, and the one I choose between the existing ones is the XFAM. This technique has been implemented in some programs already as Abacus, but as we know, it does not solve coupled problems. So, how does the XFAM works? In the XFAM, some functions are added permitting the correct representation of the displacement field. In the first picture, you can see the fracture or the discontinuity, and in the graph, it's possible to see in the displacement field if it was used only the finite element, there is a linear transaction in the second element, as seen in the continuous line. And when we add the extra equations of xfin, we obtain the shape that we want, which is a discontinuity in the displacement field. So, how these equations are added? This is made adding in the interpolation of the displacement field some functions. The first part of this equation is the standard finite element displacement, and the second is the enriched part of the displacement, where we can have many types of functions. If we have a discontinuity, we can use a function called half-side in the length of the fracture and a tip crack function for the singularity generated in the tip of the fracture. We can also use a function called sign distance function for the transition of materials. So the method of enrichment is based on adding functions to reproduce some features in the finite element mesh. Some advantages of the xfin method is that we don't need a very thin mesh to represent the features in it, and the fracture doesn't need to match the edges or the nodes of the finite element mesh. It can cut the element, as you can see in the picture here. Here are some results we had, and we can see a fracture in the middle of the pictures. And now we are on the phase of propagating the fracture, but we still have some problems of the stress field. But we are almost finished the validation of the problem. And our next step is to put a fluid to open the fracture. So after that, we have another steps. The first is to finish the coupled analysis. We have only to validate it. And the next step is to do the problem for multi-phase problems. And next we try to start with a pre-existing fracture in the mesh and intersect it with another fracture and see what happens with the stress field. And finally, study what happens with the propagation of fractures when we have different materials. And I'd like to thank you to Universidade of Brasília, to the University of Strathclyde, to the GREAT project, and Professor Manuel Porfírio Cordoneto, and to Professor Alessandro Tarantino.